Um, yeah, and George, we just put the audio on here, so anytime you're ready, you can go right ahead.
Okay, great. Can you hear me?
Yes, we hear you clearly.
All right, wonderful. Okay, I cannot see my. Can you see my cursor on the screen?
Uh, no, we don't see your cursor. We do see your slides.
That's okay. That's fine. All right. Okay, yeah, thanks everyone. Thanks for the invite to give this talk on the Magnetars and the FRB connection. So we're starting a new session. And this session will be kind of devoted to really digging deep into the Magnetar class and their FRB connections. So my talk is going to be a little bit of an overview. But yeah, again, thanks. I'm learning a lot from this great conference, and I'm very envious of all of you radio astronomers for all of the great discoveries you're making. And we're only trying to catch up. So I'm a high energy astronomer. I am based at NASA Goddard, so this is going to be biased towards X-rays and a little bit of gamma rays. Um, Okay, so you've seen some variations of this, of course, when we talk about pulsars and magnetars. This is the first thing that we show. This is the famous PP dot diagram. And very immediately, it kind of comes to you that there are separate classes in this population of neutron stars. So what we are interested in today is the population that is on the top right. These are what we call magnetars. So they have, classically speaking, periods between like 1 and 10 to a little bit over 10 seconds. They have large spin down rates, and if we assume magnetic dipole breaking, this translates to dipole fields that are 10 to the 14 Gauss on average, and young spin down ages of the order of a few kilo years to a few tens of kilo years, again on average, with quite a bit of spread. Their spin down luminosity is also on the lowish side. But the more interesting element is that, as I will show in a second, this E dot cannot really explain their bright X-ray luminosities. So far, we've discovered about 25 to 30. This is a little bit maybe outdated, the 25 number. So we have about 30 discovered magnetars. They all reside close to the plane, so that gives you an idea of their or a confirmation of their young ages. Also, some of them are within centrally located within X-ray bright supernova remnants. Again, confirmation of their bright ages. So we haven't found a very convincing case for a magnetar in a binary. This is in contrast to, for instance, some of the models that are proposed for long period transients. But that's an interesting question. And as I said, they're bright X-ray emitters, typically stronger X-ray emitters than regular pulsars. They have hot surfaces with a temperature of about 0.5 keV, which is quite a bit larger than normal pulsars at similar ages. So this is kind of a distinction between the two. And of course, some of the magnetars are radio pulsars, radio loud pulsars, about 25% or so, 6 so far, if I'm not mistaken. And perhaps the most striking element of magnetars and something that separates them and what was used in the first place to basically establish the magnetar population is their variability. And they are varying over 10 decades in time scales and energy scales. So it's a staggering time domain type sources. All right, so here what I'm showing is basically the X-ray luminosity as a function of the spin down. The yellow line is the one-to-one relation, and the red dots and bars are basically for magnetars, and this is simply to establish that most of the magnetars, either in outburst or in quiescence, which is what the dot shows, they have X-ray luminosity larger than E dot. So you're going to have to go and find another energy source, and the most natural, obviously, is their B field. So you take from that magnetic energy flux and you kind of transform it or convert it into radiation. And that could be done through decay of fields, and that work has been done for a couple of decades now. That's of course different than the regular pulsars are shown in gray dots here. Of course, if you ask, for instance, how much energy does a magnetar pack, it could be quite a bit, varying between 10 to the 46, 10 to the 50, and that's not to say, at the early stages of their birth. So because of that, they have been kind of thrown into the mix of many different time domain transients, for instance, gamma ray bursts, superluminous supernova, ultraluminous X-ray sources, and of course, fast radio bursts. So they're very appealing to explain extreme phenomena because of that energy that they can pack. And of course, we're still kind of looking for the smoking gun evidence for many of these classes, but we know that in the case of fast radio bursts, as I will discuss later on, that has been, in a way established. Okay, so magnetar transient phenomenology. This is really kind of an overview again for the things that are of interest to this talk, and of course, basically what makes magnetars magnetars. So let's go through this. One of the, I would say, perhaps telltale signature of the case of a magnetar when you know in any type of source is if you detect what we call short bursts from that source. So these are typically on the order of 100 milliseconds to 200 milliseconds. They're SED peaks in the hard X-rays around 10 or 20 keV. Their spectrum is thermal, so it's kind of a fireball plasma emitting some energies. And they're bright. They can reach energies of about 10 to the 40 or 10 to the 41 if we're speaking in energy scale. And of course, that's quite bright for large field of view hard X-ray monitors to detect like Swift-Bat Fermi GBM. And this is how we in fact discover most of the magnetars. And these bursts could come in storms. So you could have, for instance, in this case, about 20 minutes or so, a little bit less, 200 bursts from the famous Galactic Magnetar 1935 plus 2154. So that was in towards the end or maybe April 2020. And this has been detected about 7 times so far since the, let's say, the mid-1980s or something, or maybe even earlier than that. So they're a little bit on the rare side to see the storms. At the time of these bursting activity, including the storms, what you see is that the X-ray emission from a magnetar increases, sometimes by as many as several orders of 2 to 3 orders of magnitude. And that's what we call outbursts. So basically you have the bursting activity and then you have the outbursts. The outburst evolves in a typical manner. It decays back to its quiescent state most of the time over the course of months to also a couple of years or so. And during that time, you have a lot of activity going on. On top of that, at the start of typically for the ones that are continuously monitored, at the start of an outburst, you observe some sort of a timing anomaly. Typically, it's a glitch. And that kind of tells you that there's something connected between the internal and the external of the star that is kind of driving all of these interesting behavior. And of course, for several of the magnetars, as I mentioned before, some radio emission has been discovered. Typically, that's kind of concurrent to the X-ray activity, not simultaneous in a way. So on the lower left side, I'm showing the flux density from XEJ 1810, I believe. And you can see that it started quite a bright radio pulsar and then decayed towards quiescence several years after. So, and of course, this is not the only transient activity. I'm skipping over giant flares and a few other elements. So this is not the end of the story, but just to kind of give you a flavor of what's going on. Okay, so since the discovery of FRBs, of course, Magnetar has been at they were at the forefront of the kind of let's say the progenitor of FRBs, and you can kind of understand why. You can pack lots of energy in very small volumes, and you need that because FRBs were quite bright, and also their short time scales indicate that probably where the emission region is quite small, and so magnetars obviously are a natural explanation for FRBs. And of course, that kind of, let's say, was one of the perhaps, I don't know what people think about it, but since the discovery of FRBs, one of the most important discoveries, in my opinion, was, of course, the FRB from the Galactic Magnetar SGR 1935 plus 2154. So this on the left, you are all familiar with what I'm showing. This is a chime double burst from the source that happened in April 2020. And of course, that kind of can, okay, you have the answer. Indeed, magnetars can produce FRB FRB-like emission. Maybe at the time it wasn't, it was at the tail end of the brightness, but you could see it to extragalactic distances. So if this was from whatever few megaparsecs, you would have seen it and you would call it an FRB. So you got your answer. But of course, that now allows you to perform more rigorous tests of a whole lot of other questions. So for instance, now you could, now knowing what the progenitor is, you can perhaps look deeper into the question of what is their triggering mechanism? What is the plasma properties at the time of the FRB emission? Is there any relation with the X-ray activity? What about the other magnetars? Are we just simply missing them because we're not observing them, or was there something special about this case? And of course, now that we know that they are correlated, you could basically go into asking the question of how they are related to extragalactic FRBs, both repeaters and non-repeaters. You could look at that question from a qualitative type of analysis. Well, maybe I shouldn't say qualitative, but basically what I mean is, are the polarization properties of FRBs, similar in a way to the polarization properties of some of these birds that we've discovered from 1935 and other magnetars as well, of course. So you could look at it that way, and of course there's the population analysis, asking ourselves what we know about the magnetar population, what we know from that one single data point. Also, it's still a single data point, but it's something. What does that translate in terms of explaining the extragalactic FRB population? So many talks have already covered some of this, and also please stick around for the rest of the session. There's going to be, in fact, what I would argue the more interesting talks that I am simply kind of introducing the landscape for. So, all right. So some of the questions that I laid out were immediately answered. Some, an hour or two later. It was quite remarkable that in my opinion, that the radio burst occurred simultaneous to an X-ray burst. So this is, you hit two birds at the same time. So you, not only FRBs are connected, or FRB-like emission connected to magnetars, but they're also connected intimately to the X-ray activity. The X-ray activity has occurred since 1979, and so we've had time to study it a little bit. So that gives us, more constraint into what's happening in the magnetar environment, in order to kind of trigger FRBs and where they come from. So that was excellent. And of course, another element that we should always keep in mind is the fact that the FRB occurred perhaps, I believe, 13 hours after the massive and the largest burst storm that SGR 1935 has shown. So SGR 1935 was active for about 13 hours. You cannot see my cursor, but the middle panel over there, the very left, a tiny black bar, a zoom in of that is the bottom panel, and that's basically the burst storm. And then it calmed down quite a bit. So the burst storm, we've detected hundreds of bursts with NICER and with Fermi, GBM, and SwiftBat. None of them had shown any FRB, and then the FRB occurred just hours later, but the source had died down quite a bit. So what does that mean? Is it just simply coincidence? I don't know the answer to that, but that's something to keep in mind. So we had a lot of answers to that. And then, of course, once you had that beautiful bright X-ray burst, you could perform spectral analysis on the burst. And also, I'm not mentioning the temporal analysis, but you could perform spectral analysis on the burst and compare it to the rest of the bursting activity that occurred that day. And what we found, and others, of course, has found the same thing, is that spectrally, the FRB-associated X-ray burst was a little bit harder. So let's say the SED extended to a larger range of energies, as you can see on the top panel over there. So the dashed line is a simulation of the FRB-associated X-ray burst, and the other is an example, a very, let's say, normal, like basically most of the burst, other than the FRB-associated one, showed that type of spectral behavior. So you see the difference hitting you in the eye. So what does that mean again, right? I'm not going to go into the details, but many people have thought about this heavily, and you've got plenty of references there to kind of refer to. And I'm sorry, I'm missing a lot, I know. Since that burst, of course, many radio bursts were detected from, define many, I guess. But several radio bursts were detected from SGR 1935 and its activation. It goes in and out of activation since 2014, since its discovery. But on the top, you will have basically the radio burst episodes that I have been able to collage or put together. And the green ones are the ones that have X-ray associated bursting activity as well. So not only the FRB happening in 2020 April, but also there are other ones that we had seen some X-ray activity from. And so it seemed, and of course, these radio bursts were several orders of magnitude weaker than the FRB. And so if the X-ray to radioluminosity kind of scales proportionally, then in that case, it's perhaps not very surprising that we did not detect all of them in X-rays. And of course, we don't have full sky coverage in X-rays as well. So the fact that we've discovered many of them, in my opinion, tells me that likely all radio FRB-like bursts are coincident with X-ray bursts. And the overwhelming majority of X-ray bursts are not coincident with radio bursts. And people can speak to that. There has been many deep observations in 1935 and long coverage with radio to only discover one or even null. So of course, kind of if somebody could collage all of that information, not only looking at the population of radio bursts from 1935, but also bring in all of the X-ray bursts, which is probably not an easy task because you'll have to contact multiple teams. These X-ray bursts have been detected by CONUS Wind, the Russian Space Telescope Integral from the Italian Space Agency, HXMT from the Chinese Academy of Sciences, and from GBM from NASA in the US. And so you have to contact all of these people and kind of bring them all together. But I think it would be very useful because you would be able to kind of answer some questions about whether indeed the radio to X-ray luminosity ratio, is it constant? What is the scatter there? Is it very tightly, for instance, correlated, or there's a lot of scatter? All of that is extremely important. For the same X-ray luminosity also, do you see the same curvature in the FRB associated burst compared to the others, or is it really different for the same luminosity we're talking, okay? So all of that will give you very excellent ideas for what's going on. But indeed, you need to kind of contact. So you got to be social, and perhaps coming from a neutral country, so maybe Canada or Luxembourg or whatever. But some people can do this. Okay, so I'll mention one more thing about 1935. So this happened in October 2022. So we had the second brightest radio burst. So that would be the dashed line in red, basically at 0, detected by CHIME as well. So 1935 was in an active state again. And so the top panel in what you're seeing here is basically the burst per minute. So we're talking about a burst every minute on average for about 2+ days before the FRB was detected. This is a zoom in on a longer monitoring in X-rays, by the way. That was like a 20-day something monitoring in X-rays. And the bottom is basically the X-ray count rate, or a proxy for luminosity, how bright the source was. And immediately you can see that there was a flare in X-rays just before the FRB occurred, but the FRB occurred towards kind of like the tail end of the flare. But what was fascinating to us is what was happening in the timing, which basically provides you an idea with the internal but also the external dynamics of the source. So we believe that changes in nu dot is related to kind of how much wind is escaping the star, and that relates to how much open field lines you have. So that would be the third panel that you're looking at there. And during about 10-hour period surrounding the FRB, you had a massive nu dot, the largest ever discovered by an order or 2 orders of magnitude compared to any pulsar. And during that period, smack in the middle of it, there was the FRB. And we would expect many open field lines during that period in order to get to that nu dot. That's all speculation. It's for the theorists, but that all of that is various clues that brings you closer to understanding the FRB phenomenon from the Magnetar progenitor perspective. And there's a lot of physics going on here. I'm not going to go into that. Perhaps not necessarily related to FRBs. And the last thing that I want to mention is basically the population. And so that's when you start basically asking the question of, and people have looked into this plenty before we started looking into this, but the question of how connected is the extragalactic FRB population to the Magnetar population in the galaxy, and that starts with understanding the Magnetar population in our galaxy first and foremost. And so this has been done slightly before, but never really involved starting to constrain the population from an observational perspective. And we set out to do that. A team of scientists, that would be a PhD student, my postdoc, and some collaborators, Daniela here on the call as well, who helped quite a bit in this. But so basically we incorporated the observational constraints. We predominantly discover magnetars through their bursting activity, so we incorporated that into the modeling. We treated XMM as a survey. We see 0 magnetars discovered through the XMM survey. Sorry, yes.
Hey, George, just to let you know, 2 minutes.
Thank you. Yeah, almost done. And through that, we've been able to, and of course, we have to match the observational properties of the population, like PP dot, log n, log s, and that's what you're looking at here. And we've been able to kind of get observational constraints on some of the parameters. The one that matters perhaps the most for the FRB case is basically the birth rate. And so we've been able to get a birth rate in the fraction of neutron stars, roughly speaking, about 10%. But I will say that this is a strict lower limit, and the case for that is because in our modeling, with quite a bit of assumptions, and you can go look at the paper for those or ask me, but we basically, for this first work, we said that we would detect every single outburst with the current large field of view high energy monitors, which is not the case, and we know it's not the case. And so, and of course, our results show that the magnetar population that we simulate that matches the observed one actually does not match the heliocentric distribution. It's actually galactocentric, and that tells you that we're missing something. So we're working on a more complete model, incorporating the sensitivity of SwiftBAT and other missions to kind of get a better idea of that fraction of magnetars born at neutron stars. So it will be somewhat larger than the 10% typical number. By how much, I cannot really tell. 20 to 30%, I don't know, but we shall see. And then from there, you can basically, and the model also incorporates a more detailed prescription of the bursting activity. And then from there, you can go and ask yourself, okay, what does that mean for the FRB population? So that's a long work in progress that we're trying to kind of perform more rigorously. So let's see where we get. Okay, I'll leave you the summary. I'm gonna tell you that X-rays are expensive. They don't easily come. We mainly provide you with upper limits, which I apologize for. But there are things that one could do. Heavy continuous radio monitoring of magnetars and outbursts. That's extremely important if possible. Also in quiescence, because we don't know what they're doing. We only observe them typically in outbursts. And we miss a lot also. So if it's possible in quiescence, that'd be great. And then the rest, if we can do stuff from the X-ray world, that would be great. There are some interesting mission proposed, but we shall see. The landscape is changing under our feet as we speak. So hopefully we're lucky in the meantime. So thank you.
Okay, questions for George? We'll do Sujay first.
Hi, Sujay Marte from RRI, Rahaman Research Institute, Bangalore. I have a question about the X-ray detectability. So you're saying, are we limited by FOV or are we limited by the sensitivity? Like if you have all sky coverage right now, given the X-ray to radio ratio, we'll be able to detect all of them, or we do really need more sensitive detectors?
Thank you. I think we are limited by both. So we certainly know that we are limited by sensitivity because we do see an extension. If you look at the log n, log s distribution of the bursts with Fermi or SwiftBAT, and then if you look at the ones with XMM or nicer, you do see an extension of that log n, log s.
Sorry, George, can you repeat? I think you were there was an issue with the internet.
Oh, I apologize for that. Can you hear me better now?
Yes.
Okay. So what I was saying is I think it's a combination. It's the two together, but mainly sensitivity. So, but that comes also with, if you want to become more sensitive, it's difficult to have a larger field of view. But I'll tell you that if you look at the log N log S distribution with Fermi GBM or Swift-BAT, which are large field of view monitors, and you look at the ones from NICER, you will see that the log N log S actually extends down to below the sensitivity of Fermi and Swift, which tells you you're missing quite a lot because it's a steep log N log S. So you want to gain in sensitivity, but that unfortunately kind of lowers your field of view unless you build this humongous telescope. Yeah, it's not easy. But what I will say, perhaps just to finish up, is that radio bursts most of the time have happened from 1935, close to quite active periods. And that's when we observe them mostly with X-rays. So if you have a monitor that can just look at 1935 and afford looking at it during activity, and not only 1935, other magnetars, that would be the best strategy. So you have an outburst and then just stare at it. And that's what HXMT did to catch the beautiful X-ray burst associated with the FRB. So there are ways around it, and it's not easy. Yeah.
There's time for another question, but maybe the next speaker could start to set up. Right behind you. Oh.
Hi, this is Sachin from McGill. So there was a recent coherent burst from Carina Nebula that we all heard about during this conference. Was there any X-ray activity associated with the burst from Carina Nebula?
Thank you. Shout out to Kaustubh who performed all of that analysis. We looked for X-ray activity from the source with Fermi because of its large field of view, and with Swift as well, and we could not find any. In fact, I believe actually now I know for sure the source. I remember. The source was in the field of view of Fermi GBM, and we did not detect any bursts in Fermi GBM. The LX over LR is not very constraining because the radio burst was a bit on the weaker side. So if we're lucky and we detect more bursts from that source that are a bit brighter, maybe these upper limits start becoming tighter and tighter, and then a comparison with 1935 becomes more meaningful. But yes, down to the limits of Fermi and Swift, we do not see anything.
Okay, I think we have to move on to the next speaker. Thank you very much, George. Okay, next speaker, Marcus Lower from Swinburne on the title you can see in front of you.
Thank you. So yes, I'm Marcus Lower. I'm an ARC DECRA fellow. Oops, I'm not sharing. Oh, just classic. Yeah.
Sorry for that.
No more subtitles. All right. Yes, I'm Marcus Lower, ARC DECRA fellow at Swinburne University, and today I'm going to be telling you about some interesting emission that we saw from an extraordinary radio-loud magnetar, partly on behalf of the Parkes P885 magnetar monitoring team. The magnetar I'm talking about today is, of course, 1E1547 minus 5408, not SGO 1935. Now, this magnetar was actually found way back in the 1980s by an ancient telescope called the Einstein Observatory, not Einstein Probe, where it was discovered, catalogued as an X-ray point source, and kind of forgotten about for a few years, until Gelfand and Gainsler noticed that its X-ray flux was quite variable, and they suggested that it was possibly a magnetar candidate embedded in this radio shell, which you can see on your left. That's a much more recent ASCAP image of the supernova remnant. It was then observed using Murray-Yang by Fernando Camillo and friends, and they found that that this source was actually a radio pulsar spinning once every about two and a bit seconds. And that its high spin down rate confirmed that, yes, it was in fact a magnetar. And in fact, it's the second radio-loud magnetar to be discovered after 1810. What makes this magnetar a bit unique amongst the other radio-loud magnetars is that we've been conducting an almost continuous 18-year monitoring campaign using both Murray-Yang 64-meter Parkes radio telescope and the Swift XRT. So on your left, what I'm showing there on the top is the X-ray flux over a very long time span, going from 2007 all the way to about 2025. And you can see, it's undergone several X-ray outbursts during that time. The bottom panel is showing the spin down rate as a function of time. But what I want to draw your attention to is the sort of gray band along the bottom there. That's kind of giving you a sense of the fraction of time that the magnetar is seen to be active in the radio. And it has been more or less active all the time. Every time we point parts at it, we see it in the radio. So this is the only persistent radiolab magnetar that we know of to date. And with 18 years of observations, you find that it can kind of do anything. If you can think of any kind of pulsar phenomenology, any kind of pulsar thing, this magnetar does it. It has pulse profile shape variations, glitches, spin down rate variations during outbursts, and then pretty much every single kind of emission state switching that you can think of. It's got nulling, state switching. So yes, so there's a lot of this data is currently unpublished, and we're going to be looking at it at some point. But the data I'm talking about today was all collected shortly after the 2009 outburst. So this began back in January 2009, where the X-ray flux shot up by about a factor of 2 to 3 orders of magnitude, and it was followed up extensively by pretty much every high-energy telescope that was out there at the time. During this period, its radio emission switched off very briefly, then came back, then switched off, and did all sorts of crazy stuff. And one in particular cool thing was that there was similar to SGI 1935, there was a coincident detection of a 3 sigma coincident detection of an X-ray and a radio outburst that was seen in a joint observation taken by X-Minhajur and Maria. And that's reported in this work by Israel et al. From 2021. A few days after the outburst began, so about a month after it began, we also saw this unusual little transient component pop up. Now, as far as magnetar outbursts go, that's pretty normal. Their profiles change all the time. We see new components appear and disappear. That's not that unusual. This was only seen in our X-band observations taken using the Mars receiver on Parkes. Unfortunately, the data we have is only fold mode, so we're averaging over between 9 to 12 rotations of the magnetar for each subintegration. I guess I can point out this transient component's highlighted in that little pink square on the left. So that's on the left is showing pulse phase versus time. You can see you've got kind of regular magnetar emission and then this sort of intermittent component. If you look at sort of a waterfall diagram of what the sort of spectrum of this transient component and the more regular emission looks like on the right, again, you can see broadband emission for the magnetar, pretty normal, but the transient component, if you squint, has kind of some interesting looking features. And if we look at the individual subintegrations containing the emission from this component, from this transient component, what we notice is that almost all of the bursts, if you could call them that, are very narrow band. Some of them are only like a few pixels in these pictures that I'm showing. Now, these are real. These aren't radio frequency interference. They only show up within a very narrow phase window. And they also all show the same kind of diffractive scintillation that we see in the broadband emission. Whereas the interference, you'd expect to see it across all pulse phases. It shouldn't be in phase with the rotation of the magnetar. We also have a few subintegrations where we see what could have been multiple component bursts, but because, again, we're averaging over several rotations of the magnetar, it's unclear whether these are single events that have multiple components or whether these are just individual bursts that we've just averaged, that have been averaged together, which is unfortunate. So in this work, we are sort of still treating these possible multi-component things as individual independent events. In terms of their properties, we've extracted their spectra and we've run things like the running power law model that was used in the Time FRB catalog 1 to look at the spectra running. Unfortunately, doing a bit of an apples to apples comparison between the results of that by running that on this magnetar and the other sort of narrowband emitters like the Crab pulsar and SGR 1935, it's a bit hard to do one-to-one comparison because, as you can kind of see, the scale on the x-axis and y-axis of these plots are very, very different. And this just comes down to this really comes down to the observing frequencies that these bursts were detected at. In terms of maybe a bit more informative, looking at widths versus spectral extent, the kind of distribution of widths and spectral extents kind of follow that, what was seen for the repeating FRBs in the Chime FRB catalog. And I saw there was an update yesterday for the catalog too, which looks probably, this looks a little bit more like what's seen in the Chime FRB 2 catalog 2, which is kind of nice to see. In terms of polarization, the bursts are in general mostly highly polarized. There is a bit of diversity in terms of the fraction of linear versus circular polarization. Some of them look a little bit over-polarized, and that's partly because of some artifacts in the data, as well as some questions about our calibration. So in general, that appears a bit different to what's seen in the sort of polarization fraction distributions for several repeating FRBs. So there is a bit of a difference there. But of course, repeating FRBs, as we're now starting to find, are also quite diverse in their polarization properties as well. Sticking with polarization, this here I'm showing is a series of average pulse profiles. This is many, many rotations averaged together, seen on different days. And you can see its polarization was changing quite a bit over this sort of 10 to 20 day period. This is also seen at some observations at different frequencies. So drawing your attention to the position angle swing in the top panels of each of these plots, you can see the position angle swing was quite variable. The very first observation, it's even going the opposite direction to all of our subsequent observations. And then the sort of lines that are overplotted, those are the rotating vector model fits. So, we can kind of see that the rotating vector model does somewhat match the position angle swing as it evolves over time. However, if we then look at this middle panel here, the implied angles between the spin and magnetic axes is incredibly variable, much more than you'd expect for, a very simple dipole that could be kind of quite stable with time. So this implies that we're either seeing some sort of variable changes in the magnetic and viewing geometry of the star, in which case the mechanism behind that's a bit unclear. It could be something like free precession or twisting of the magnetic field, or it's also possible that the rotating vector model is just not a good match to this data. In which case we'd need a bit more, something more complicated to try and explain what's going on. I just want to end on this other little kind of, what's maybe a minor point of interest. So we've now got 4 minutes. We've now got 4 known narrowband emitters of radio bursts, kind of in and around our galaxy. You've got the Crab pulsar, SGR 1935, the Crab's LMC twin, BO540-69. These are all, young, energetic pulsars associated with supernova remnants, and that is kind of interesting. I don't really know what to make of that in terms of, does this imply that repeaters are related to these objects? Maybe. But if that is the case, then we are starting to kind of build up a small, at the moment, population of galactic-ish BO540s not in our galaxy, it's in the LMC, population of repeating FRB analogs, which might tell us a bit more about, the mechanism responsible for the repeating FRB emission. So just to end, I think I've hopefully convinced you that 1547 is a truly extraordinary magnetar. It does everything, as I said. For a very brief period of time, we saw this transient component appear where it was emitting quite band-limited radio bursts. The bandwidths are comparable. Bandwidths and polarization properties are comparable to other narrowband emitters, and there are some similarities to repeating FRBs. This coincided with some dramatic changes in the magnetic field topology that we don't fully understand at the moment. And this raises, of course, this interesting question of, is this magnetar yet another galactic FRB analog? The emission properties kind of imply that maybe there's a similar emission mechanism. However, of course, this still doesn't account for the whole issue of these bursts being 10 orders of magnitude less luminous than genuine FRBs. And I also want to point out that the P85 project on Parkes is very well poised to capture the next outburst from this object and any other magnetar that goes bang and over the next few years. So thanks for your time, and I'm happy to take questions.
We've got a question online. Oh, you need this?
It's in the chat. Yeah, so there's a question in the chat. Hi, Pranav here from MPRFR in Bonn. Do you have any statistically significant hold on only the highly linearly polarized FRB-like components of this magnetar? And do they show distinct polarization and spectral properties?
That is a very good question. I can say for the position angle swings for the highly linearly polarized bursts, they don't follow the same rotating vector model tracks that we've plotted against the broadband emission. They're kind of just scattered all over the place. Yeah, otherwise, let me go back a few slides. I mean, again, these things are kind of a bit scattered all over the place. There's no kind of real, they don't like cluster as well as like the repeating FRBs in terms of polarization fraction space.
Okay, question from Younes.
Thank you for a very interesting talk. I agree with you. There's so many exciting things going on in this pulsar. You could talk in this magnetar. You could talk about it for an hour. But may I ask something about this the narrow band features that seem to appear at a certain pulse phase? Now you have a coherent timing solution, I imagine, for over 18 years, or coherent enough. It's connected. It seems connected anyway. It's fine. But if you just looked at these, could you find the periodicity from these?
Oh, that is a good question. I'm not sure. Unfortunately, again, this is fold mode data. So I guess for this observation, we see quite a few bursts. I can imagine you might be able to get a periodicity, but like an RAT. But yeah, that would be if we saw it again do this, that would be a good thing to test. Thanks.
Hey, time for one more question. Lose your laptop.
Thank you. Thank you. I'm Matteo from INAF in Italy. Another question regarding the narrowband burst. I mean, I couldn't appreciate the scale because it's
a bit hard to tell.
There's a millisecond.
Yes, these are all a
time.
few milliseconds wide.
Okay. Do you have like high resolution data to see if there are, substructure like Saturn moons?
Unfortunately, no. Even there was one observation we had simultaneous fold mode from the analog filter bank. But aside from the fact it was an analog filter bank and the data is not very good, the time resolution was even worse. It was like 2 millisecond integrations instead of, well, time samples instead of 1 millisecond. Yeah.
Okay, let's thank our speaker again. The next two talk are the first one will be by Jun-Shuo Zhang on Stringent Constraint, Magnetar, magnetic energy, and FRBs.
Great. So yeah, anytime you're ready.
Okay, can you hear me? And can you show my screen?
Yeah, you can hear it.
Okay. Okay, now I'm going to start. Hello everyone, my name is Jun-Shuo Zhang, a PhD student at NAOC, surprised by Dili and Pei Wang. It's my honor to present our recent work on FRB 2024 on behalf of the Fast Key Science Project, providing the most stringent constraint on magnetic energy of magnetars as an energy of fast FRBs to date. Okay. Now, since Chenhui Niu has already given a nice overview of FAST, I won't go into the details again. And just mention the sensitivity of the FAST help us to capture the more bursts of the FRBs. And the FRB Key Sense project is one of the major large programs at FAST. So far, it has detected over 26,000 bursts. And here's some active repeater, and the work I'm presenting here is based on about half of them. And here's a brief timeline of the basic information of FRB 2024-01-14A. The source was first discovered by Cham, and thanks to the VOE network and ATEL, the discovery was rapidly circulated. We decided to follow up quickly as the source appeared to be both bright and hyperactive, and later on we detected a few bursts, and which we reported on the ATEL. About a week later, Meerkat team localized the source precisely and identified its host galaxy. So we calibrated the fastest pointing position since then. And on March 5th, we captured the burst storms and reported it on the ATEL. Follow-up observations with the GTC telescope, including work of Zhang from our FRB Key Sense project collaboration, measured the photometric redshift for this source. And here we present the fast observations of this most active repeater up to now. We carried observations between January and August in 2024 and maintained a nearly weekly observation cadence over a span of 214 days and 34 hours of on-source time in total. And during this period, the average burst rate was about 220 bursts per hour. And at the peak, the burst rate reached an astonishing level of over 700 bursts per hour. This is the highest rate ever recorded. And all the bursts were identified using a SNR threshold of 12. This corresponds to a sensitivity of roughly 26 millijansky milliseconds. We identified two major active phases during this period. The first started from the March to April, and the second happened to between July and August. During our observation period, we found that this FRB remained active for the entire 8 months. In total, we detected 11,553 bursts, which means we have collected the largest dataset of repeating bursts to date. We calibrated the flux density and energy for each burst, and as shown in the time energy counterplot, 2 major burst storms are clearly visible. In addition, we did not see any significant trend in the daily median energy all over the observation. As Jerry New has just mentioned, observations have shown that Magnetars are a source of FRBs, and so far the Magnetar channel is the only known mechanism that can produce FRBs. The strong energy release from this source allows us to place constraints on the Magnetar as a central engine behind these bursts. We estimated the total equivalent energy and emitted during our observation period by scaling it according to the duty cycle of our observations. Assuming a typical radio efficiency of about 10 to the -4, and taking a global beaming factor of 0.1 in consideration, we found that the total emitted energy is about 1.47 times 10 to the 47 Earth. Compared with other active repeaters reported so far, the energy is more than 30 times higher. It is also around 86% of the total dipole magnetic energy stored in a typical magnetar. If the current rate of the activity continues, the magnetar may run out of valuable magnetic energy in just about 1 more month. As a magnetic moment of a magnetar can be estimated through the equation shown here, we provide a lower limit on the magnetic moment of the central magnetar. The value we derive is about 9.4 times 10 to the 32 Gauss cubic centimeter, as shown on the right-hand axis of this figure. Our result places a strong constraint on models that assumes a low radio efficiency, such as non-magnetosphere models. It also challenges models that rely on large beaming factor within typical magnetar parameter. To match the observational data, the central engine must either emitted within tightly constrained parameters, or it must be a more powerful compact object than a typical magnetar. We also examined burst rate's distribution of the energy, and we identified a characteristic energy around 10 to 37 erg. As shown in the plot, the burst rate tends to decrease when the energy falls below the EC and clearly deviates from power law behavior. We perform a power law thesis with increasing the energy thresholds from the EC and found that the power law phase indices didn't converge to a consistent value. This indicates that a single power law model does not describe the overall distribution very well. We also examine the log normal fit and the bimodal log normal fit on this distribution. We noticed that the residuals and the normalized Pearson coefficient shows deviations in simple log normal fit. In addition, statistical tests indicate that a single log normal fit performs worse than the bimodal one. These results suggest a bimodal structure in the distribution. This, in turn, may imply that there are multiple burst populations or distinct emission mechanisms in repeating FRBs. We also plotted the corner plot between observational parameters, parameter pairs, but no correlation were found except flux density, bandwidth, and pulse width, all of which show positive correlation with the burst energy. This is expected as energy is derived from these parameters, so they are naturally coupled. The first KSP collaboration has also conducted a comprehensive analysis on this repeater, including polarization, periodicity, and morphology. Results on arm variation, Faraday conversion, and so on were just reported in Tianzong Wang's talk. And Deng and Zhou search for the periodicity on both short and long timescales using multiple methods. As a result, we identified 3 sub-second period candidates and a potential 68-day activity cycle, and several QPO candidates. The QPO candidates exhibit a strong correlation between the central frequencies and widths, suggesting a potential universal quality factor. This may be related to magnetar cluster oscillations or Arvan wave instabilities. Furthermore, multiple QPOs appears to evolve dynamically over time. These findings help to clarify the observational basis in previous studies, where QPO detections were sometimes attributed to the spin period of compact objects. Longxuan Zhang analyzed the statistical properties of burst morphology. The burst.
Just to let you know, sorry to interrupt. 2 minutes.
Oh, okay. Based on the bursts are classified based on the morphological features and the frequency drift rates. The significant statistical differences are observed between the upward and downward drifting clusters. Okay, here's a summary of my report. Our 4 works on energy budget, polarization analysis, periodicity searching, and the burst morphology will be available soon as a preprint on the archive. And thank you for your attention, and I will be happy to take any questions. Okay, I'll stop here.
Okay, thank you very much for the very interesting talk. We have questions. We'll start with one from online.
Thanks. This is from Pranav in Bonn. The question is, did you also investigate whether the bimodal distribution observed in burst energies is correlated with the classification of bursts into clustered and Poissonian types based on their wait time distributions?
I will come back to the. So that's a great question. We do analyze the waiting time distributions, but haven't analyzed the bimodal energy distribution with a waiting time distributions yet. And we will try it later. Thank you.
Any question?
Thank you. Hi, I'm Marilyn Cruces from UC Chile. I was wondering regarding the 68 potential activity cycle that you mentioned, and for what I read in the slides, was inferred from Lom's cargo and from folding. Do you have those results?
Yeah, this work is mainly developed by Deng Zhou, and as far as I know, he used epoch folding and lob struggle to verify this 68 per day activity cycle, but we only observed this source using 200 days, so there are only two or three phases for this result. It is not so solid. If you want to know more details about this, I will talk to Dunker and for your questions.
Okay, one more.
Thank you.
Yeah, so Zora, what are you seeing, University of Maryland, NASA Goddard? The QPOs you find, do they have harmonic ratios of the frequencies like you'd expect from crustal oscillations, or are they sort of randomly placed in frequency space, the QPOs?
Okay, I have no idea with these questions, and so I will look transfer the questions to Dunker later, and I will talk. I will talk with you in the Slack.
Yeah,
Thank
well,
you.
he was just asking if the if they're harmonically related. The QPOs, are they if you took the ratios, are they integers of the frequencies? Or you could talk later. That's okay. Okay, sorry. Okay, let's thank the speaker again.
Thank you. Okay, I stop it.
The next speaker will be Sheikh.
Can I share my screen now?
Yes, we hear you.
Yeah. So can I share my screen now?
Yeah, go ahead and share.
Okay, on ultra strong Magnetar.
Okay. Can you see my screen now?
Yes.
Yes, we can.
Okay. So can I start?
Yes, please do.
Okay. Hi, everyone. This is Minhajur Rahaman. I'm a postdoctoral fellow at the Open University of Israel. And today, I'll be talking about the implications for Magnetar progenitors from persistent radio sources of fast radio burst. So for the purpose of this talk, I'll be focusing on the most studied case, well-studied case of PRS, which is the PRS associated with FRB 121102A. Now to start with, we can have a basic summary of the observational facts regarding this. So from radio imaging, you have an upper limit on the size, which is 0.7 parsec. From radio scintillation studies, you have a lower limit on the size, which is 0.03 parsec. And given the shape of the spectrum and the redshift of the source, and employing an equipartition analysis, assuming a synchrotron origin for the persistent radio emission, we have an equipartition radius of 0.1 parsec, which sits comfortably in between the lower size limit and the upper size constraint that we have. So if you combine all this together, you get a very important and crucial ingredient in identifying and selecting a particular kind of magnetar progenitor. So basically, what you have is a very compact PRS. Now, if you are trying to understand the PRS in a magnetar kind of a framework, what is the picture that you have in mind? So the picture is something like this, that if you follow my cursor, here we have a magnetar central engine, which is giving rise to the streams of charged particles, which is in fact confined by an expanding supernova remnant. So post-confinement, it is a population of trapped, highly energetic, hot, electrically charged particles, which is forming what is referred to as the magnetar wind nebula. And it is synchrotron radiation from this magnetar wind nebula, which is the candidate for the persistent radio emission. Okay, so this is the region number 2 in this particular schematic, labeled as magnetar wind nebula, which is the candidate for the persistent radio emission. The other thing that you can immediately see from this schematic is that if you consider the outer radius of the magnetar wind nebula, that is in fact equal to the inner radius of the supernova remnant. That means if you have a constraint on the size of the magnetar wind nebula, you have indirectly a constraint on the size of the supernova remnant itself. In fact, we can actually flip this around and say if you have a size constraint of the supernova remnant in any kind of a progenitor model, you also have a constraint on the size of the magnetar wind nebula, which in fact is the size corresponding to the PRS that you just saw in the observations. Okay, so then for a magnetar progenitor model, we can ask this question: what has been the most popular magnetar progenitor model in the literature? And the answer, it turns out, is a millisecond magnetar. So the references that you see on the screen are not supposed to be exhaustive, but rather it is meant to be illustrative in showing you that this has been a popular candidate for around a decade. Now, given the compact size of the source that we just saw from observations, we can actually put this millisecond magnetar progenitor model to the test. And what is the test that you can put this to? We can ask a very simple question. We can ask the question, say, suppose in this particular framework, what is the time that is required for the supernova remnant to expand to a size of around 0.1 parsec, correct? And that time would correspond to the age of the source. For a millisecond magnetar, the time it takes for the supernova remnant to actually expand to a size of 0.1 parsec is close to 2.5 years. It's less than 3 years. And it is not surprising why this is so. Because you see, if you have a magnetar progenitor kind of a system, that suffers from a rapid spin down, and almost 10 to the power 52 ergs of energy is deposited to the supernova remnant. And irrespective of what was the initial explosion energy associated with the remnant, this deposition of 10 to the power 52 ergs of energy, it will actually boost up the expansion velocity of the remnant, and it would very quickly reach this size of 0.1 parsec and beyond. And now I want to point to this important fact that since the observation of the first burst of the FRB 121102, which by its very name was in the year 2012, we have 13 years that have elapsed till now. That means if you are considering a PRS associated with an FRB 121102 powered by a common magnetar progenitor model, it at least has to be 13 years old or longer. But clearly, if you see this number for the millisecond magnetar progenitor model, this time scale of 2.5 is much less than the 13 years time that you would actually require on the very least. So then you can ask this question, okay, fine. So the magnetar model with a millisecond magnetar progenitor does not seem to work if you take the compactness of the PRS into account. But now, if you look at the second line of the solution, it is suggesting a different kind of origin. So what is the origin that is being suggested here? So here it is referring to a sub-energetic scenario. So what does it mean? So you saw for the millisecond magnetar, you actually had a very rapid expansion of the remnant. And that's the reason that you have very less time given the compact source size to actually reach that size. But now, if you consider a scenario where the expansion velocity of the remnant is very low, and that would correspond to a supernova explosion energy of around 10 to the 50 Earth and a mass in the range of 10 solar masses, which will give you a very slow expansion velocity. And it is not surprising, given the slow expansion velocity, for the same size, you are actually reaching an age which is up to a few decades. So given that this particular scenario actually allows for longer and a wider parameter of ages that is possible for the system, this is the scenario that you advocate for in our work. So we already saw about the compactness of the PRS, but we still have to explain what actually powers the PRS. So to do so, what we have to know is actually what is the energy content in the nebula itself. Because to remind you, it is the charged particles in the nebula which is powering the PRS. So to go back to our equipartition analysis, we actually have an equipartition energy of 10 to the power 49 erg. So just to remind the audience, the equipartition energy is the minimum energy that is required for explaining a given set of synchrotron observables like the spectrum and the luminosity. So in principle, you need energy equal to 10 to the 49 or larger. Now, what you can look for is that how the nebular energy content changes as a function of time for the rotation loss channel, which is shown as a purple line here on the figure. So here you see, if you trace the purple line, it first rises and then peaks. So it peaks at the characteristic spin down time scale, unsurprisingly for the rotational loss channel. And then the energy content due to the rotation channel actually comes down. And this can be understood in the frame of adiabatic losses, because the magnetar wind nebula that you have is not a static thing. It's actually expanding and pushing on the supernova remnant. So with time, the energy content of the nebula is going to go down because of this PDV work done on the supernova remnant. So you see, if you now put a horizontal line corresponding to this energy of 10 to the power 49 ergs, you can quickly see that for the rotational channel, you can satisfy energy content in the nebula of 10 to the power 49 ergs or higher only for about a decade. That means if your system is actually older than a decade, your rotational channel is actually saturated, it's quenched. And you need an alternative reservoir of energy to actually sustain the luminosity. And that alternative reservoir of energy turns out to be the internal magnetic field decay of the magnetar. Okay. Now, in fact, if you're when you're talking about this internal magnetic field decay, one is the energy reservoir itself. What is the strength of the internal magnetic field that you have to ask? And the second question that you have to ask is what is the decay timescale associated with it? So just by the illustration that you see here, if you have to sustain your PRS beyond a decade, you need a time scale for the decay of the internal magnetic field, which is much larger. In fact, in such a scenario, we have a characteristic switching time in which the energetics in the nebula switches from being rotation dominated to internal magnetic decay dominated. And this switching time is almost independent of the initial spin period of the magnetar. Now you can ask this very fundamental question. Okay, given that we advocate for a sub-energetic scenario, which would actually give you longer ages for these PRS systems, what is the strongest internal magnetic field and what is the largest decay time scale that is consistent with the PRS observables for PRS associated with FRB 1211-028? And the solution space, if you look here, corresponds to this blue strip, where you can see that in this solution space, the ages that are possible for this particular system is up to 100 years. Okay. And in this particular solution space, what is more interesting is that you have clear definitive predictions for the synchrotron spectrum, which is that if you look at this dashed blue line, this would correspond to the cooling break. So which you can see from the figure itself. In this blue strip, the cooling break is supposed to be around 100 gigahertz. And if you look at the self-absorption frequency, this is supposed to be in the range of around 200 megahertz. So we have definitive predictions for this model.
Hey, just a little over a minute and a half left.
Thank you. So this has to be actually contrasted with the traditional magnetic powered models that has been proposed in the literature, where the decay time scale is actually taken to be around a few months. So in these kind of models, there is no way to actually differentiate between a rotational power channel and a magnetic power channel, simply because of the fact both the spin down time scale and the decay time scale is of the same order. So almost all the energy is being released in over a decade, and there is no energy left for older systems. And this, again, this set of references is just illustrative and not exhaustive, just to say that the small time scale thing has been referenced here. And the largest time scale that we come to around 500 years is closer to the decay time scale of internal magnetic field that we do see for a galactic magnetar. So this is in kind of a not only a consistency check, but also a new kind of a paradigm that has been proposed here. So to summarize, this millisecond magnetar seems to be unlikely candidates for the PRS FRBs. The rotation power channel for the PRS is quickly quenched within a decade, and it is only the internal magnetic field channel that can be sustaining this PRS for up to a century. And for a PRS which is born in a kind of sub-energetic kind of a scenario, we have clear predictions for the spectrum, namely a cooling break at around 100 to 150 gigahertz at a flux value of roughly 35 to 40 microjansky, and a self-absorption frequency at the very low frequency at 200 megahertz at a flux value of around 180 to 200 microjansky. So with that, I'd like to end on this quote that all models are wrong, some are useful. So with these predictions, let us make the Magnetar model useful. Thank you very much.
Hey, thank you very, very much for that talk. Time for some questions. Okay, we'll go to Casey. Can I throw this?
Hi, this is Casey Law from Caltech. I was interested in if you had any predictions for the potential for long-term radio monitoring to constrain this model, or if there's any variability expected on decade timescales that we can measure.
Yeah, so that's a very good question. So essentially, so if you have a slow injection of the internal magnetic field, your flux values are supposed to remain steady for almost few decades. So in fact, you can do a long-term radio monitoring of the base level flux. So I'll just maybe minimize this and show this. One minute. Okay. Sorry. Sorry. So there's some problem. Just trying to get rid of. Okay, so if you go to the long-term flux monitoring, you could actually do a chi-squared kind of fit, which I'm just trying to get here. 1 minute.
Okay, thank you.
Okay.
Sorry. Yeah. So yeah, so just 1 minute to do so. So you can do a long-term flux monitoring. So this is a plot from our paper, which shows that if you have long-term flux monitoring, you can actually constrain this temporal index alpha F, which would actually give you a constraint on the birth of this kind of systems. So for our sub-energetic scenario, we would actually have ages. If you fit this kind of model, it will come to birth ages of around 100 years.
Okay.
Okay, thank you. This is Duncan Lorimer from WVU. Nice talk. My question is perhaps to all the audience, but to you right now is how does this compare, these PRS models compare with the 300 odd supernova remnants that we know in the Milky Way? Like how unusual would they be? Would this model be in the context of those remnants? Do you see what I'm saying?
Yeah. So can you see my screen?
Yes.
Yeah. So the basic idea is that, that you have synchrotron radiation from this wind nebula. And now for the supernova remnant in our, if it was indeed the case that you had so much energy in the supernova remnant, you are born with very luminous, very high luminosity. So these PRS have bolometric luminosity in the radio band around 10 to the power 38 ergs per second. So that radioluminosity is directly proportional to the energy content. So if you indeed had such kind of systems in our own galactic supernova remnants, you would actually see very luminous sources.
Thank you.
The last talk of the session will be by Andrea Geminardi on the searching for transient radio emission from galactic magnetars.
Hi, everyone. I am Andrea Geminardi, a second-year PhD student at USPavia in Italy. And in this flash talk, I will briefly describe Northern Cross observations on 7 galactic magnetars for a total exposure of 560 hours. The Northern Cross is a transit radio telescope located near Bologna in Italy. It samples the sky with a time resolution of 138 microseconds over a bandwidth of 14.8 megahertz, centered at 408 megahertz. The current configuration of the telescope corresponds to an RMS sensitivity of roughly 1 Jansky, and as you can see in the dark region of the plot, this is enough not only to detect FRB-like events from the targets, but also giant pulses like emission and the most energetic pulses from pulsars and rotating radio transients. In our campaign, we didn't detect any radio bursts directly associated to magnetars, but we exploited our observations to set upper limits on both the burst rate and their energy distribution. Here in the plot, you can see as a color map the rate of detectable events predicted by our power law energy distribution model, and that is function of two free parameters that are the slope of the distribution on the x-axis and the normalization of the power law on the y-axis that corresponds to the rate of events with energy greater than the FRB-like event emitted in 2020 by SGRJ 1935. And the take-home message of this graph is that as we increase the slope of the power law, our limit becomes stringent and stringent on the burst rate. And if we compare our results with other observations on magnetars, for example, the ones performed by Chime in 2020, we can see that our work is consistent with there only if we assume that the power law slope is lower than 1.4. And if we take into account also Northern Cross observations on nearby galaxies, we can find an even more stringent limit. And if I can leave you here my conclusions, and let me just emphasize that we constrained the power law and to be less than 1.4, and also this result is somewhat in tension with the models that tries to explain the whole sky rate of FRBs only using radio bursts from magnetars. And if you are curious about the details of the work, you can scan the QR code and check the paper, and thank you for the attention.
Okay, thank you very much. So time for a question. Yes.
Hi, Marilyn Cruces from UC Chile. So sorry, I'm not quite familiarized with the observing setup. Can you go back a few slides? So what's the bandwidth observing frequency? Okay, so it's low frequency.
Yeah, it's low frequency, centered around 408 megahertz. And actually, we, as you can see also in the graph, we look for a maximum duration of around 75 milliseconds. So burst with a maximum duration of, yeah, we are sensitive to not only FRB-like events, as I said.
Yeah. Thank you.
Sure. Thank you. Miles Sherman from Caltech. I was wondering if you tried to, this is kind of a follow-up question, but I was wondering if you tried to reconcile your results with high frequency observations or monitoring of magnetars and nearby galaxies as well.
With respect to to high energy observations, unfortunately, our 7 magnetars were not active at higher energies during our campaign. This campaign was performed from January 2024 to January 2025, and we can also compare our campaign with these other similar campaign performed at the same frequency, actually, that are these ones. I don't know if...
Thank you.
Okay, okay, and I guess it's time for coffee right now. So, and we return at 3:40. Was it 3:40?
3:45.
Oh, sorry, 3:45.